Alright folks, we're back with more double integrals. Last time we were trying to find the volume of a surface over a rectangular region, okay? So we got a formula for it, a symbolic formula that wasn't much good to us if we were trying to calculate, okay? And that was the following. We got that the volume is supposed to be equal to this double integral, whatever that means. So volume is equal to the double integral over the region of the surface f of xy dA. Okay, so the question is, what does that mean when you have a rectangular region that you're integrating over? So here's a rectangular region and we have some surface over it, and we're just maybe like a slide or something else, whatever that is, and we're just trying to calculate the volume of that surface over this region. So that's going to be our next theorem. Our next theorem says, well, it's not so bad if your function is continuous over this rectangle. So right now we're only doing rectangles. And let's say the rectangle is AB cross CD. So x is from A to B, y is from Z to T. Then this volume, okay, this volume was equal to this. Well, what is this integral over a region? Okay, what does it mean? Well, it says you look at your boundaries, okay? So my y boundaries are y equals c to y equals d, okay? So I write f of xy dy because this is the range of the y. And then after I integrate this, I need to do x equals a to x equals b, and I need to do the integral with respect to dx, okay? Now these are partials, which means when I'm doing this integral, everything that's an x behaves just like a constant. And when I'm doing the outside integral, everything that's y behaves like a constant. Now, since we're over the rectangle, okay, there's something neat, is that you can switch the order of integration if needed without any cost. What I mean by a cost we'll see later on when we do regions that are not rectangular. But without any fear, you can switch them around. So I can just switch the integrals around, and I can switch the dx and dy around. Okay, so much for a formula. Let's get down to an example, okay? Let's say I'm interested in the surface xy squared, whatever that looks like, okay, over the rectangle 0, 2, 1, 3, okay? So here, if we go back to here, so it's going to be from 0 to 2, 1 to 3, okay? So all we have to do to calculate the volume is apply the formula. You say 0 to 2, x squared y squared dx. And where does y go? Y goes from 1 to 3. That's why y is on the end. So if you write these, you'll never get confused. If you write, well, this is the boundaries for x, then the first one has to be a dx. These are the boundaries for y. Then the outside one has to be a dy. Now, what we're actually doing is we're actually doing this integral first. Okay, so we're doing this integral first. Which means, well, this is not that bad of an integral. Remember, everything that has a y, it behaves like a constant. So this is just like, 5x or y squared x, right? So the integral is going to be x squared over 2. So you have y squared x squared over 2. Now, x range from 0 to 2. So I have to evaluate this guy from 0 to 2. Okay? Now, the outside integral stays. Now, I'll do my evaluation. When I plug in 2 to x, I get 4 over 2, okay, y squared. And when I plug in 0, of course, I get just 0, don't I? Now, okay, so now that has turned the integral all into only y's. All the x's now disappeared. So I have 1 to 3 to y squared dy, which is not that bad. That's just 2/3 y cubed. You remember, increase the power by 1, divide by the same number. Evaluate from 1 to 3. And once we do the evaluation, I get 52 over 3. You can check my math later on. Alright, now, if I wanted to switch the order of integration, what could I do? Well, I can switch the places. Now, y is going from 1 to 3. So it's going to be the function dy, okay? And on the outside, x is going from 0 to 2. And So on the outside, we're going to have a dx. Okay, so if I integrate it this way, it should really give me the same answer. Note, you can only do this on a rectangle, okay? So it's very important that switching is for free. You can just switch their places when you have a rectangle. You can't do that in general. So what does this mean? Well, we're taking this integral first. Okay, we're taking this integral first. This integral, we're integrating this with respect to y, so everything that's x behaves like a constant. Integral of y squared is y cubed over 3. We keep the x because it's a constant. Evaluate from 1 to 3. So we're going to plug in 1 to 3 wherever we see a y, right? This is y equals 3 because it was dy. Y equals 1. We don't plug it into x, we plug it into y. So once I plug it into y, I'm going to get 3 cubed is 27, so 27x over 3 minus 1x over 3. Okay, very good. So we get 26 over 3x dx. X is going to be evaluated from 0 to 2. So integrate that. That's going to be x over 2. In other words, it's going to be 26 over 6. 3 times 2 is 6. 0 to 2, plug it in, and you again get exactly the same answer, which was 52 over 3. Okay, so this is neat. At least over rectangular regions, we can calculate volumes now. Now, of course, the burning question is, well, what if you don't have a rectangular region? What if your region is really messed up, okay? What if you have a weird region? Then what do you do? And that's what we're going to do next. Okay? So, volumes over general regions. Let's say we are trying to find the volume under the surface z equals f of xy over region R. And now R is not a rectangle, it's just any old region. Now we know that the volume is always going to be this, okay? The double integral over the region of the function, okay? So how do I interpret this? How do I change it into good old double integral when the region is not rectangular? Now keep in mind, just like single variable calculus, the surface has to be continuous over this region R. We want a continuous surface over the region R, and we want R to be a closed region. Closed region means it has the boundaries are included in the region. Okay. Now you can generalize it just like we did with improper integrals to regions that are not closed or when the function is not continuous, but that's beyond the subject of this class right now. So what do we do when R is not rectangular? So here I drew two cases. I have a weird R. Okay, so here is the weird R. It's not rectangular at all. But what I have is the following. I can say the top curve, this curve, is some function of x, I call the g2 of x, and this bottom curve that bounds it is another function of x, I call it g1 of x. Okay? So then I can say that the integral is again, oops, sorry, it's not. I messed this up. Sorry, this is not dA anymore. This is dy dx. My bad, guys. Okay, the second one is correct. Okay, so this double integral, which was the double integral of the region, double integral of the region of the function over the region R of the function f of xy, what is that equal to? Okay, well, what that is equal to is very simple. I'm going to do vertical cross sections first. Okay, so I'm going to look at this vertical line. Okay, so it's not vertical, so it's supposed to be vertical. So I'm going to do, so y changes from the bottom curve is g1x, the top curve is g2x. So y goes from g1 to g2, top, bottom, okay? And x goes from a to b, dy, dx. Okay, very simple. We'll talk why that is in a second. Now, I'd like to make a note here, and the note is very interesting itself. If I was not interested in any volumes or anything like that, if I was just interested in the area of this region, which is a Calc 1 question, now, the area of the region would be the top function minus the bottom function over the interval a, b. Now note that that's equal to a to b, y equals g1 of x to g2 of x dy dx. If you evaluate this just in one step, you just get this, okay? Why did I mention this? Because the only thing is, you can think about it as like we're trying to calculate the area, but because there's something over it, we plug in the height, okay? Now I'm going to talk where we get this one specifically. The idea here is over this region R, maybe there is some sort of thing, some sort of three-dimensional object like my hand. Okay, so I'm trying to calculate the volume under my hand. Okay, the question here is, in normal single variable calculus, if we wanted to calculate the area of R, not the volume but the area, all you do is you imagine the heights sweeping from left to right over from A to B. You imagine the heights. Okay, so the top minus the bottom over A to B. Okay, so that was exactly this, the top minus the bottom over A to B. Now what we need to do when we're doing volumes, okay, so I'm going to sweep this volume, whatever the surface over it is, I'm going to, instead of sweeping lines, I'm going to be sweeping cross sections, okay, cross sections. So if you think about a cross section, the cross section has a base and a height. So I'm going to try to approximate it by a rectangle, okay? So what would be the area of the rectangle? Well, it would be the base, which would be top minus bottom, times the height. What's the height? Well, that's just f, okay? So that's where the formula comes from. Again, I wish I could draw you a three-dimensional version of this with the z-axis and an actual three-dimensional object, but my Picasso-like drawing capabilities don't let me do that. So I would suggest that you take a look at your favorite calc book and see how this cross-section moving stuff works. Now we could also do the same area if the region that we had was not something like horizontal like this, but was like this, okay? Now x is described in terms of functions of h. So the left side is h1 of y and the right side is h2 of y. There's just two functions. Then if I'm trying to calculate the volume, what I need to do, y is ranging from c to d, times, this time I'm taking horizontal elements, okay? So when you're taking horizontal elements, you do right minus left. So right is going to go on top, h2 of y. Left is going to go on the bottom, h1 of y. And we're going to imagine that this is moving, these horizontal elements are moving like this from bottom to top. So y equals c to y equals d, okay? Again, that would give me a volume. That would also give me another way you can calculate the area. If I take the f of x, y out, oops, I left it in, that would just, again, be the area of the region. Okay? So it depends on which way is easier. Sometimes, as we're going to see later on, you need both ways to solve a problem. You'll see what I'm talking about in a few minutes. Alright, so now I want to go back to good old area before we get on to volume. Let's do good old area with double integrals. Now these are, of course, these all can be done very simply by single integrals. The point here is we're trying to get our some exercise on double integrals. So I asked the following question. I would like you guys to find the area of the region bounded by y equals square root of x and y equals x cubed. Okay, so here I drew the functions. This would be y equals x cubed, okay, and this would be y equals square root of x. Okay, so y equals x cubed actually goes down like this, but where it's bounded is going to be this region. So this is the region R. The first order of business is trying to find where they intersect, okay? So if you solve them side by side, you set x cubed equal to square root of x and solve it, you'll see that it has two solutions, which we already know. They equal when x is equal to 0 and when x is equal to 1. Okay? So let's try to calculate the area of this region using double integrals. Top minus bottom. What's on the top? Y equals square root of x. What's on the bottom? Y equals x cubed. Okay, so that's going to be a dy because we're talking about y. On the outside, where does x go? X goes from 0 to 1. x goes from 0 to x goes to 1. So these vertical elements are going sideways from 0 to 1, and then I'll get the, when they sweep the whole region, I'll get the area. Okay? So let's go over the setup once more. Y is going to go from the bottom is x cubed, this function. The top is square root of x. Okay? That's going to be a dy. And x goes from 0 to 1. Okay? So once we do that, okay, this is very easy. Obviously, this is the integral of 1. So integral of 1 is just y. So we end up with 0 to 1. Y, there is no dy. Y evaluate like this. Sorry, that dy is extra. Okay? Once we integrate it. Okay? So what is that? Plug it in. These are y equals x cubed and y equals square root of x. So plug into y, you get square root of x minus x cubed. Well, that's exactly how you would do it in Calc 1, right? You would say top minus bottom over 0, 1. So you would think, you know, this is really stupid. Why did you do these complicated two steps first? The reason is because we have to, when we're calculating volume, when we're calculating areas, okay, we don't need to. We can just skip to this step and write it like this. But what I'm trying to say is you don't need to be afraid of the notation. When you do the integration, it's just top minus bottom. So I evaluated for you, and we got the answer 1. Now, if we wanted to do horizontal elements like this, okay, then the right side was what? It was y equals x cubed, so it's going to be x equals cubic roots of y. Okay, so if we solve this, y equals x cubed for x, what do we get? We get that the right side is cubic roots of y, and this guy on top was y equals square root of x. So y equals square root of x means x equals y squared. So if I'm doing horizontal elements, again, when x is equal to 1, y is equal to 1, so they again intersect on the vertical side 0 to 1. Okay, so this is y, not x. It came out to be symmetric because we picked up a nice problem. And x is going to go from y squared to x is going to go to cubic roots of y. Okay, right minus left. Right is cubic roots of y, left is y squared, dx dy. Okay, so when we do that, of course, once you integrate, you're going to get, right, cubic root of y minus y squared dy. I skipped a step. You can go home and do it. And I would like you guys to continue this exercise, find the actual answer, which is not hard, right? And see that it is actually 1. Okay, so that's that. Now, let's move on to a proper volume example. Let's say, this is going to be a great question, guys, so pay attention. Let's say I'm trying to find the volume under this surface, x times e to the y cubed, oh my goodness, it looks horrible, over the region R, and I drew you the region R. The region R is bounded by the line y equals x over 2, okay, and y equals 1. Okay, so what I'm going to do is, everybody likes vertical elements. I'm going to write the volume using vertical elements. Remember, what was the volume? Volume was the double integral over the region f of xy dA. Okay, so now we're going to do, okay, top minus bottom. So the top is just y equals 1. The bottom is y equals x minus x over 2. Okay, and we're going to evaluate this. They're going to intersect at 0 and 2, right? Because y equals x over 2. When y is equal to 1, x is equal to 2. So x ranges from 0 to 2. Then we have the function f of xy, which was x times e to the y cubed. First dy, then dx. Now, which means we have to integrate this guy. Okay? Now remember, x is a constant. We're only interested in stuff that has y in it, e to the y cubed. Do you want to integrate e to the y cubed? I don't think so. It's hard, right? Okay, so we don't want to integrate e to the y cubed. So I'm here thinking, oh, this is a really tough integral. How do you integrate e to the y cubed? Okay, then I get this idea. Why don't I do, when somebody gives me an integral like this, double integral like this, and I have no idea, it's so hard how to do it, why don't I just look at the region again, and instead of doing a vertical element, let me do a horizontal element. Okay, so I got the same region again, y equals x over 2, but I'm going to write everything in terms of y now. When y is equal to x over 2, that means x is equal to 2y. Okay, and the left hand side is, of course, this is x equals 0, right? So the horizontal element, right minus left. Right is x is equal to 2y. Left is x equals 0, the y-axis. Okay, and where is this going to range? Well, the horizontal elements are going to go from bottom to top. So they're going to go from 0 to 1. Okay, so again, right minus left. Okay, right hand point is x equals 2y. Left hand point is of the horizontal element is x equals 0, just the y-axis. Okay, and those horizontal elements are going to go like this. So they're going to go from y equals 0 to 1. Now, that's going to be dx dy. So we changed the order of integration, but it wasn't as simple as just switching the integrals around. You see that? There was a cost to it. We have to write everything in terms of the other variable now. So there's a cost to this. When you want to switch these, you have to draw the region and see what the world looks like in terms of the other variable. So once I write this, I realize that now this is much easier to integrate than the original one. Why? Because we have to integrate this. Okay, Brock, it's still the same thing. Okay, I know it's still x e to the y cubed. But this time I am integrating with respect to x, not y. So this whole ugly thing is just a constant. It's just like a number like 5 or something like that. We're just integrating x. Integral of x is x over 2. X squared over 2, sorry. So we have x squared over 2 times, this behaves like a constant, e to the y cubed. X goes from 0 to 2y. So I'm going to plug in 2y wherever I see an x. We plug it in. We're going to get 4y squared over 2 e to the y cubed. And when I plug in 0 minus, I just get a 0. So now all I'm trying to do, once you simplify the 4 and 2, it goes down to 2y squared e to the y cubed dy. Okay? Now you might think, Burak, this is just as bad. This is horrible. Actually, it's not. Because this is good old substitution, right? If you let u be equal to y cubed, then du would be 3y squared, and I have a term like that. I don't have 3y squared, I have 2y squared. The way I like to do these is I'll just multiply it by 3 over 3. I'll multiply the whole integral by 3 over 3 so that I don't change it. Okay? I'll get rid of the limits of integration because I'm going to change them to another variable anyways. So now this 3y squared dy is du, right? This is just du, 3y squared dy. So what's remaining is we have a 2 over 3, and this guy, e to the y cubed, guess what? It's just e to the u. Okay? So integrating e to the u with respect to u is very easy. Integral of e to the u is just e to the u, right? It's just constant with itself. So nothing changes. So we have 2 over 3 e to the u. Now, I always go back to the original variable. So I plugged in what u was. U was y cubed. We have 2 over 3 e to the y cubed. Evaluated from the limits of integration were from 0 to 1. So we just get 2 over 3 e to the minus 1 times e to the minus 1. Sorry, 2 over 3 times e minus 1. Now, guys, this is an important thing. Sometimes when an integral is very, very hard, like this integral, if you draw the region and figure out that it was, say, a vertical element, go to a horizontal element, okay? Or if it was a horizontal element, go to a vertical element, an undoable integral immediately becomes sometimes a doable integral, okay? So finally, I would like to conclude the lecture by writing down some properties. These are really analogous to single variable integrals. We're going to take two continuous functions f and g over a closed interval r, and c is a constant. So if I want to find the integral of the sum, that's just sum of the integrals. Same thing for differences. So if you have two functions added, you can separate out the integrals. Same thing if they are subtracted. If you have a constant times a function, well, you can just pull the constant out of the function. Okay? And if one function is bigger than the other function, then the integral of the bigger function is going to be bigger than the smaller function. Okay? So if the function is bigger, the integral is bigger as well. And finally, if I divide my region into two pieces, okay? So if I divide R into two pieces, R1 and R2, the integral over R is the same thing as the integral over R1 plus the integral over R2. So those are the general properties, the general tricks that you can use. Next time we're going to go into techniques of integration for double integrals. I'm just going to do one, which is substitution. So substitution, remember, was the easiest one when we were doing single variable calculus. Substitution is a little bit harder when you're doing multivariable calculus. So next time we're going to do that, hopefully. Take care. Bye-bye.